The journey of sand begins with weathering, the process that breaks down large rocks into smaller particles over millions of years. Weathering can be categorized into two main types, physical and chemical. Physical weathering. This type involves mechanical forces that break rocks into smaller pieces without altering their chemical composition. Common physical weathering processes include freeze-thaw cycles. Water seeps into cracks in rocks, freezes, and expands, causing the rock to break apart. Thermal expansion. Temperature fluctuations cause rocks to expand and contract, leading to fractures. Abrasion. Rocks grind against each other, especially in rivers and glaciers, breaking into smaller particles. Chemical weathering. Chemical reactions alter the minerals within rocks, leading to their breakdown. Key processes include hydrolysis. Water reacts with minerals, forming new compounds and weakening the rock structure. Oxidation. Minerals, particularly those containing iron, react with oxygen to form oxides, which are more easily broken down. Dissolution. Acidic water dissolves minerals, especially carbonates, leading to the rock's disintegration. Once rocks are broken down into smaller particles, these particles are transported by natural forces such as rivers, wind, and glaciers, leading to the creation and distribution of sand. Rivers. Flowing water is a powerful agent of erosion. Rivers carry sediment from their sources in mountains to their mouths at the sea, eroding the landscape and creating sand along the way. The sediment is sorted by size, with larger particles deposited first and finer particles carried further downstream. Wind. In desert environments, wind plays a crucial role in transporting and depositing sand. Wind can carry sand particles over long distances, creating dunes and other aeolian features. Glaciers. Glacial movement grinds rocks into fine particles, including sand. As glaciers advance and retreat, they transport and deposit these particles, contributing to the formation of sand deposits. The transported sediment eventually settles and accumulates in layers, leading to the formation of sedimentary rocks through processes called sedimentation and lithification. Sedimentation. As sediment is transported by rivers, wind, and glaciers, it eventually comes to rest in various depositional environments, such as riverbeds, beaches, and ocean floors. Over time, these layers of sediment build up, with older layers buried beneath newer ones. Lithification. Over geological time, accumulated sediment undergoes compaction and cementation. Compaction occurs as the weight of overlying sediment presses down, squeezing out water and reducing pore spaces. Cementation involves minerals precipitating from groundwater and binding the sediment particles together, forming sedimentary rocks like sandstone. The primary mineral in most sand is quartz, a durable and resistant mineral composed of silicon and oxygen. Quartz's resistance to weathering and its abundance in the Earth's crust make it a common component of sand. Other minerals, like feldspar and mica, can also be found in sand, though they're less common due to their susceptibility to weathering. Quartz. Quartz is chemically stable and resistant to weathering. Its hardness and durability allow it to persist through multiple cycles of erosion and transport. The high silica content of quartz, CO2, also contributes to its stability and prevalence in sand. Other minerals. While quartz dominates, other minerals can be present in sand depending on the local geology. Feldspar and mica, for instance, are more susceptible to weathering but can contribute to the sand's composition in certain regions. The relatively uniform size of sand grains is a result of the natural processes that break down rocks and transport particles. As particles are transported by rivers, wind, and glaciers, they undergo abrasion, which rounds and smooths them, leading to relatively uniform grain sizes. Abrasion and sorting. During transport, sand particles collide and rub against each other, gradually becoming more rounded and uniform in size. This process is influenced by the energy of the transporting medium. High-energy environments, e.g., fast-flowing rivers, produce coarser sand, as larger particles are broken down less. Low-energy environments, e.g., calm beaches, produce finer sand, as smaller particles are more easily transported and sorted. Deposition. As sediment settles, it is sorted by size, with coarser particles deposited first and finer particles carried further. This sorting process leads to the relatively uniform grain sizes observed in sand deposits. The Earth has been undergoing continuous erosion for billions of years, shaping its surface and contributing to the formation of sand. This immense timescale, spanning eons, allows for the gradual breakdown of rocks into smaller particles. Precambrian era, the earliest rocks, formed over 4 billion years ago, have been subjected to weathering and erosion, contributing to the earliest sand formations. During this era, primitive continents began to form, and the processes of erosion started breaking down these landmasses into smaller particles. Paleozoic era, as life diversified in the oceans and later on land, the landscape continued to evolve. The erosion of ancient mountain ranges and the formation of extensive sedimentary basins led to the accumulation of sand in various depositional environments. Mesozoic era. The age of the dinosaurs saw significant geological changes, including the breakup of the supercontinent Pangaea. This tectonic activity created new mountain ranges and sedimentary basins, contributing to the ongoing production and distribution of sand. Cenozoic era. The most recent era, starting about 66 million years ago, has seen the continued uplift and erosion of mountain ranges like the Himalayas and the Andes. These processes have produced vast quantities of sediment, including sand, which have been transported and deposited in various environments. The movement of the Earth's tectonic plates is a major driver of sand formation and distribution. Plate tectonics not only shape the Earth's surface but also influence the processes that create and transport sand. Mountain building. When tectonic plates collide, they create mountain ranges through a process called orogeny. These mountains, composed of various rock types, are subjected to weathering and erosion, producing sand-sized particles. The Himalayas, for example, are still growing today due to the collision between the Indian and Eurasian plates. Rifting and basin formation. When tectonic plates diverge, they create rift valleys and sedimentary basins. These basins accumulate sediment, including sand, from the erosion of surrounding highlands. The East African Rift and the Basin and Range Province in the United States are examples of such tectonic settings. Subduction zones. In areas where one tectonic plate is forced beneath another, intense volcanic activity and the creation of deep ocean trenches occur. Volcanic rocks, once eroded, contribute to sand formation. The Andes Mountains and the Pacific Ring of Fire are prime examples of subduction zones impacting sand production. Climate plays a crucial role in the type and rate of weathering and erosion that produces sand. Different climates lead to varying weathering processes and sediment characteristics. Tropical climates. In tropical regions, high temperatures and abundant rainfall accelerate chemical weathering. This leads to the formation of clay-rich soils and sand. The intense weathering of feldspar and other minerals in tropical climates results in a higher concentration of quartz in the resulting sand. Arid climates. In desert environments, physical weathering predominates. The lack of moisture reduces chemical weathering, and temperature fluctuations cause rocks to fracture. Wind erosion is significant, transporting and depositing sand over vast areas. The Sahara Desert and the Namib Desert are examples of regions where arid climates shape sand formation. Temperate climates. In temperate regions, both physical and chemical weathering occur, leading to the production of a variety of sediment types, including sand. Rivers in these regions transport sediment from mountainous areas to coastal plains, where it accumulates and forms sand deposits. The rock cycle illustrates how sedimentary rocks, including sandstones, can be weathered and eroded to produce new sand. This recycling process ensures a continuous supply of sand over geological time. Weathering of sedimentary rocks. Sedimentary rocks, formed from the compaction and cementation of sand and other sediments, can be broken down through weathering. This process releases sand-sized particles back into the environment, contributing to the ongoing cycle of sand formation. Metamorphic transformation. Under certain conditions, sedimentary rocks can undergo metamorphism, transforming into metamorphic rocks. When these rocks are exposed to surface conditions, they can be weathered and eroded to produce sand. For example, quartzite, a metamorphic rock derived from sandstone, can break down into quartz sand. Sedimentary rock cycle. The continuous formation, erosion, and deposition of sedimentary rocks, including sandstones, highlight the dynamic nature of the rock cycle. Ancient sandstones, formed from older sand deposits, provide evidence of the long-term recycling of sand through geological processes. Sand is found in diverse environments across the globe, from deserts and beaches to riverbeds and ocean floors. The widespread distribution of sand is a result of the interconnected nature of Earth's systems, where weathering, erosion, and deposition occur continuously and globally. Deserts. Deserts are major sources and sinks for sand. Wind-blown sand forms dunes and other aeolian features, creating vast sand seas like the Sahara and the Arabian Desert. Beaches. Coastal environments are characterized by the accumulation of sand along shorelines. Waves and currents transport sand, creating dynamic systems where sand is constantly eroded, transported, and deposited. Famous beaches like those in Hawaii and the Caribbean are examples of such environments. Rivers and deltas. Rivers transport sand from mountainous regions to deltas, where it is deposited as sediment. These deposits can create extensive sandbars and floodplains. The Nile Delta and the Mississippi Delta are prime examples of river systems contributing to sand distribution. Ocean floors. Sand is also found on the ocean floor, particularly on continental shelves and slopes. Marine currents and waves transport and deposit sand in these underwater environments, creating sandbanks and other features. Quartz, a key component of most sand, is known for its remarkable chemical stability. This stability is a crucial factor in the uniformity of sand, as it allows quartz grains to endure various weathering processes without significant alteration. Resilience to chemical weathering. Quartz is composed of silicon dioxide, CO2, a compound that is highly resistant to chemical weathering. Unlike minerals such as feldspar, which can break down into clay minerals through hydrolysis, quartz remains largely unaffected by chemical reactions with water and acids. This resilience ensures that quartz grains remain intact over long periods, contributing to the consistency of sand. Resistance to dissolution. Quartz does not easily dissolve in water, even in acidic conditions. This property allows quartz grains to persist in environments where other minerals might dissolve and be washed away. The persistence of quartz in various depositional settings helps maintain the uniformity of sand deposits. Quartz is one of the hardest minerals, ranking 7 on the Mohs hardness scale. Its hardness and durability are key factors in the uniformity of sand grains. Resistance to physical abrasion. The hardness of quartz makes it resistant to physical abrasion during transport. As sand grains are carried by rivers, wind, and glaciers, they collide and rub against each other, gradually becoming rounded and smooth. Quartz's hardness ensures that it retains its size and shape throughout this process, leading to a uniform grain size in sand deposits. Survivability in harsh environments. The durability of quartz allows it to survive in a wide range of environments, from arid deserts to turbulent riverbeds. Its ability to withstand mechanical weathering ensures that quartz grains remain a significant component of sand, regardless of the local conditions. This survivability contributes to the widespread presence and uniformity of quartz sand. Quartz is one of the most abundant minerals in the Earth's crust, further contributing to its dominance in sand. Widespread distribution. Quartz is a major component of many common rock types, including granite and sandstone. As these rocks are weathered and eroded, quartz grains are released and transported to various depositional environments. The widespread distribution of quartz-bearing rocks ensures a continuous supply of quartz sand across different regions. Prevalence in sedimentary rocks. Sedimentary rocks, formed from the accumulation and lithification of sediment, often contain significant amounts of quartz. As these rocks are broken down through weathering and erosion, they contribute additional quartz grains to the sand cycle. The recycling of quartz through sedimentary processes maintains its presence in sand deposits. Quartz's resistance to hydrolysis, a common chemical weathering process, is another factor in its dominance in sand. Hydrolysis of feldspar. Hydrolysis is a chemical reaction where water breaks down minerals, forming new compounds. Feldspar, a common mineral in igneous rocks, readily undergoes hydrolysis, breaking down into clay minerals. This process reduces the presence of feldspar in sand, leaving quartz as the predominant mineral. Persistence of quartz grains. Unlike feldspar, quartz does not undergo hydrolysis. This resistance ensures that quartz grains remain intact and present in sand deposits. The selective removal of other minerals through hydrolysis accentuates the concentration of quartz in sand, contributing to its uniformity. The high silica content of quartz is a fundamental characteristic that influences its role in sand. Silicon dioxide composition. Quartz is composed of silicon dioxide, CO2, a compound that is chemically stable and abundant in the Earth's crust. The prevalence of silicon and oxygen, the two most common elements in the Earth's crust, ensures a plentiful supply of quartz. Stability under surface conditions. Silicon dioxide is stable under the temperature and pressure conditions at the Earth's surface. This stability prevents quartz from undergoing significant changes during weathering and transport. As a result, quartz grains remain consistent in composition and size, contributing to the overall uniformity of sand. Throughout history, humans have recognized and utilized sand for various purposes, influencing our perception and classification of this ubiquitous material. Ancient civilizations. Early societies, such as the Egyptians and Mesopotamians, used sand in construction, glassmaking, and as a medium for artistic expression. Their understanding of sand's properties influenced their appreciation of its uniformity and utility. The production of glass from sand in ancient Egypt, for instance, required a keen awareness of the consistency of quartz sand. Medieval and Renaissance Europe. During these periods, sand continued to play a crucial role in construction and manufacturing. The development of concrete, which relied on sand as a key ingredient, underscored the importance of sand's uniform grain size and composition. Renaissance artists also used sand in the creation of pigments and frescoes, appreciating its fine texture and consistency. In modern times, scientific advances have refined our understanding and classification of sand, emphasizing its uniformity. Grain size classification. Geologists classify sand based on grain size, typically ranging from 0.0625 mm to 2 mm in diameter. This standardized classification, known as the Wentworth scale, ensures a consistent definition of sand across different scientific disciplines. The focus on grain size highlights the importance of uniformity in identifying and studying sand. Mineralogical composition. Modern geology also classifies sand based on its mineralogical composition. While quartz is the most common mineral, other minerals like feldspar, mica, and heavy minerals can also be present. This classification helps scientists understand the geological history and provenance of sand deposits, further emphasizing the role of uniformity in its study. Textural maturity. The concept of textural maturity describes the extent to which sand grains have been weathered and sorted. Mature sands, characterized by well-rounded and well-sorted grains, are often composed predominantly of quartz. This focus on textural maturity underscores the significance of uniformity in evaluating the quality and origin of sand deposits. Technological advancements have expanded the use of sand in various industries, leading to standardized specifications that emphasize uniformity. Construction industry. Sand is a critical component in construction materials such as concrete, mortar, and asphalt. The construction industry requires sand with specific grain sizes and compositions to ensure structural integrity and durability. Standardized specifications for construction sand highlight the need for consistent and uniform material. Manufacturing and electronics. High-purity quartz sand is essential in the production of glass, ceramics, and silicon chips. The electronics industry, in particular, demands extremely pure quartz sand with uniform grain sizes for the production of semiconductors. The stringent quality controls in these industries underscore the importance of sand uniformity. Filtration systems. Sand is used in water filtration systems to remove impurities from drinking water and wastewater. Filtration sand must have uniform grain sizes to ensure effective filtration and prevent clogging. This application illustrates the practical necessity of sand uniformity in maintaining public health and safety. Human activities and environmental factors contribute to the perceived uniformity of sand in various ecosystems. Beach nourishment. Coastal management practices often involve beach nourishment, where sand is added to eroding shorelines to restore beaches. The sand used for nourishment is typically sourced from offshore deposits with similar grain sizes to the existing beach sand, ensuring a uniform appearance and compatibility with the natural environment. Dune restoration. In efforts to protect coastal ecosystems, dune restoration projects use sand with specific grain sizes and compositions to rebuild dunes. The uniformity of the sand used in these projects is crucial for the stability and ecological function of the restored dunes. Habitat creation. Environmental projects that create habitats for wildlife, such as nesting sites for sea turtles and shorebirds, often use sand with specific characteristics. The uniformity of sand in these projects is essential for creating suitable conditions for the targeted species. Beyond scientific and industrial applications, human perception of sand's uniformity is shaped by cultural and aesthetic factors. Art and literature. Sand has been a symbol in art and literature, representing concepts such as time, transience, and infinity. The consistent texture and appearance of sand contribute to its symbolic meaning in various cultures. Artists and writers often use the uniformity of sand to evoke imagery of deserts, beaches, and the passage of time. Tourism and recreation. Pristine, sandy beaches are highly valued for tourism and recreation. The uniformity of sand on popular beaches contributes to their aesthetic appeal and attracts visitors. Beachgoers appreciate the fine, consistent texture of sand for activities such as sunbathing, building sandcastles, and playing sports. Spiritual and meditative practices. In some cultures, sand plays a role in spiritual and meditative practices. The creation of sand mandalas in Tibetan Buddhism, for instance, involves the meticulous arrangement of colored sand into intricate patterns. The uniformity of the sand grains is essential for the precision and beauty of these sacred artworks. Sand plays a crucial role in protecting coastal areas from the forces of nature. Beaches, dunes, and sandbars serve as natural barriers against the impact of waves, storms, and rising sea levels. Beach buffer zones. Beaches act as buffer zones, absorbing the energy of incoming waves and reducing coastal erosion. The uniformity and abundance of sand on beaches help distribute wave energy evenly, protecting coastal infrastructure and ecosystems. Dune systems. Dunes, formed by wind-blown sand, are essential in stabilizing coastal environments. Their structure and vegetation trap sand and prevent it from being blown inland. Dunes act as reservoirs of sand, replenishing beaches after storms and maintaining the overall stability of the coastline. Sandbars and barrier islands. Sandbars and barrier islands provide additional protection against storm surges and high tides. These features absorb the impact of waves before they reach the shore, reducing the risk of flooding and erosion. The uniformity of sand in these formations ensures their effectiveness in coastal defense. Sand environments, including beaches, dunes, and deserts, support diverse ecosystems and are home to a wide variety of plant and animal species. Beach ecosystems. Sandy beaches provide habitat for numerous species, from tiny crustaceans and insects to larger animals like shorebirds and sea turtles. These species rely on the consistent grain size and composition of sand for nesting, burrowing, and foraging. Dune vegetation. Dunes support specialized plant communities that stabilize the sand and prevent erosion. Plants such as beach grasses and succulents are adapted to thrive in sandy soils, where their root systems help bind the sand and maintain dune structure. The uniformity of sand is crucial for the growth and health of these plant communities. Desert flora and fauna. Deserts, characterized by vast expanses of sand, support unique ecosystems adapted to extreme conditions. Animals such as lizards, insects, and rodents have evolved to navigate and live within sandy environments. Desert plants, like cacti and shrubs, have adapted to sandy soils and arid conditions, relying on the uniformity of sand for water retention and nutrient uptake. Sand plays a vital role in the natural filtration of water and the recharge of aquifers, ensuring the availability of clean water for ecosystems and human use. Natural filtration systems. As water percolates through sand, it undergoes natural filtration, removing impurities and pollutants. This process is essential for maintaining the quality of groundwater and surface water in sandy environments. The uniformity of sand grains enhances the effectiveness of natural filtration systems. Aquifer recharge. Sand-rich environments, such as riverbeds and coastal areas, facilitate the recharge of aquifers. Rainwater and surface water infiltrate through the sandy soil, replenishing underground water reserves. The consistent grain size and permeability of sand allow for efficient water infiltration and storage. Wetland ecosystems. Wetlands with sandy substrates provide important filtration and recharge functions. These ecosystems act as natural water purification systems, trapping sediments and pollutants while supporting diverse plant and animal communities. The uniformity of sand in wetlands contributes to their ecological health and water management capabilities. Sand environments contribute to carbon sequestration and climate regulation, playing a role in mitigating climate change and supporting global ecosystems. Carbon sequestration in coastal dunes. Coastal dunes, stabilized by vegetation, act as carbon sinks, storing carbon in plant biomass and sandy soils. The growth and decomposition of dune vegetation contribute to the long-term sequestration of carbon, helping to offset greenhouse gas emissions. Desert carbon sequestration. Deserts, though seemingly barren, also play a role in carbon sequestration. Certain desert plants and microbial communities capture and store carbon, contributing to the overall carbon budget. The vast sandy expanses of deserts provide a unique environment for these processes. Climate regulation by sand ecosystems. Sand environments, such as deserts and beaches, influence local and global climate patterns. Deserts can reflect sunlight, contributing to the Earth's albedo and affecting temperature regulation. Coastal sand systems influence weather patterns and ocean currents, impacting global climate dynamics. Human activities have a significant impact on sand environments, necessitating conservation efforts to protect these vital ecosystems. Sand mining and resource extraction. Sand mining for construction, glass production, and other industries depletes natural sand deposits and disrupts ecosystems. Over-extraction of sand from rivers, beaches, and dunes can lead to habitat destruction, increased erosion, and loss of biodiversity. Sustainable sand mining practices and alternative materials are essential for reducing these impacts. Coastal development and erosion. Coastal development, including tourism infrastructure and real estate, often leads to the destruction of sand dunes and beaches. This increases vulnerability to erosion and storm damage. Conservation efforts focus on protecting and restoring coastal sand systems to ensure their resilience and ecological function. Climate change and rising sea levels. Climate change and rising sea levels pose significant threats to sand environments. Increased storm intensity and sea level rise accelerate coastal erosion and disrupt sand ecosystems. Conservation strategies include restoring dunes, implementing beach nourishment projects, and protecting natural sand buffers to mitigate these effects. Public awareness and education. Raising public awareness about the importance of sand environments and their ecological roles is crucial for conservation efforts. Educational programs, community involvement, and policy initiatives can help promote sustainable practices and protect sand ecosystems for future generations.